Well, the anticipation is killing me, so I'm going to get started. All right, welcome, guys and gals and everybody. Thanks for coming. So a word about this talk and why it's titled what it is. I submitted another talk, which I just gave. Fairly simple, talk. And then John later asked if I would be willing to do a second talk. And I was like, well, the only thing I would have to talk about is this language I'm developing. And it's all vaporware, or mostly vaporware. And he goes, perfect. That's exactly what we want. And I'm like, crap. So I'm developing a language, functional programming, and this is about that language. I did not intend, I'd actually said I'm not going to talk at any conference until I get this thing released, like at 1.0 or something. It's far from 1.0. But LambdaConf is such a great conference, I decided to come, and then John roped me into it. And my title, he chose the title. So that was not my title. My title is The Ultimate Yak Shave. Because, yak shaving. This is about as bad as it gets, except maybe write a language so you can write an editor so you can write an OS in your... So anyway, let's go. First of all, it's going to be a Lisp, or it is a Lisp, because S expressions are the one true syntax. And if you disagree, you're wrong. But there is allowance made for heretics, which is there is no canonical parser. So like in Ruby and I guess Scala, I'm not really familiar with either of those. I'm a closure programmer by day. Whatever the compiler or the parser parses, that is what the language is. That is not the case for Takata. There is a grammar for the language that is defined, but it's just a data structure, actually a tree. And you evaluate that tree to produce the parser. So it's very much a parser combinator type idea. And right now I only have a recursive descent parser because it was very easy to do. Currently working on a stream parser to parse infinite streams, which is going to be kind of cool. Takata.io is the website, the domain for the language, so you can hit that up. And it's on GitHub. I haven't committed in a long time because I'm working on getting some stuff landed. You generate the parser by evaluating the tree. But you have this grammar. You could also evaluate that tree and spit out an EBNF description of the grammar. Or make a string generator that would just generate infinite numbers of strings that you can feed through the parser to see if it works or blows up. The only requirement of the parser of any parser is that it produces nested S expressions or nested list structure out of whatever you're parsing to hand off to the analyzer, because the analyzer works on this tree of nested S expressions. So you could parse Python or anything else. Anybody that wants to add or wants to have a different parser to parse a different language to plug into the Takata compilation chain is more than welcome to. And I would be glad to give any support needed. I am not going to do it. I have more than enough work on just my own ideas. But I would love to help anybody that wanted to carry that idea further. Okay, a little bit of philosophical diversion. Creativity and producing beautiful things comes about from constraints. When you put limits on what you do. An artist, a painter doesn't say, I'm just going to paint, and I'm going to use whatever paints I want. They say, I'm going to use oils, or I'm going to use watercolors, or I'm going to do pencil or whatever. And I'm not an artist, so that's the limit of what I know. But it's the constraints they place on themselves that gives rise to the creativity, because how to work around or within those constraints. So I take a lot of stuff out of Takata, and this is one of the first ones. There is no nil or null. Tony Hoare called it his billion-dollar mistake. I think he was off by an order of magnitude. I hate nils, just and null pointer exceptions. Hate them. So they're out. None of them. In fact, no, not have any exceptions. No exception handling or anything.
What happens if you divide by 0?
You core dump.
That's good.
Yeah. So, so a bit about me. Huh?
That's what we all want.
Yeah. A bit about my background. And actually, the reason I started this project was I was a Clojure programmer. Before that, for 20 years, I was an embedded programmer. So I'm used to working on the metal, basically. My idea of a high-level language used to be C or C++. And so core dumps, just like, that's what you do. But I've seen all the problems with typed exceptions and stuff, and it's like, I just want to avoid all that stuff and just, yeah.
I have a very basic question. What's your name?
Oh, that's not really important, but my name is Jim Duey, and I'm Jim Duey on Twitter, D-U-E-Y. So, okay, so yeah, really lean heavily on static analysis, even though it's a Lisp, dynamically typed, whatever you think. Lean heavily on static analysis to catch those exceptional conditions, and anything that can't be caught, you get a core dump, and then hopefully, with some cool tools that other people are working on, will make debugging that kind of error not horrible, and hopefully do a pretty good job of making it really kind of nice. Okay, so also eliminate Boolean values, and I just gave a talk about that, so I won't rehash that, but just use maybe or nothing values instead. All values are immutable by default. Your collections, just like in Clojure, there will be ways to work around it if you really had to, but that's going to be difficult because I just don't want that to be a common thing. So those are kind of the constraints or the negatives. Some of the positives. Reference counting memory management. I'm of the opinion that you can make reference counting as fast and efficient as like Mark Sweet. There's a different set of trade-offs. Being an embedded programmer, I want to eliminate the GC pause. I want to have a deterministic type of language so that you can know that you're not going to be running along and all of a sudden everything stops for a second.
So you get rid of cycle without instructions.
Do what?
That mean you can't represent cycle without instructions?
No, you can, but there's work to be done there. And so vaporware, I'm telling you, this is a lot of the answers to a lot of questions are going to be yeah, maybe, yeah. Dustin.
I thought it was impossible to create cyclic data structures with immutable data.
Laziness.
Yeah, you can do
There's laziness and some other stuff, and yeah.
Doesn't reference counted mean that anyway we get fairly close to whole world when we have a massive structure that suddenly gets free?
Yes, except you don't have to do that. So anyway, let me see if I can get through this, and if at the end we have time, ask me that question again, and because there's some cool work to do that. Okay, eliminate tail calls. That's hopefully non-controversial. But this language right now it compiles to C, which then gets run through Clang or GCC, and so depending on those guys to eliminate the tail calls. Okay, getting a little bit more into the meat of it. It is a Lisp, it is Clojure, or not Clojure. The reason I started this was I wanted Clojure, the language, compiled to native. I wanted to be off the JVM. And so I started this, and then I kept saying, well, as long as I'm doing this, I'll just tweak this little thing. And after about 6 of those tweaks, I was like, screw it, I just got to admit it, I am developing a new language. But there are some really nice ideas out of Clojure, and protocols is one of them. So all the protocol is the specification of a set of functions that work together for some purpose. They're somehow related to each other. And it really just specifies their name and the number of arguments they get. And that's the protocol. And they're defined using the def protocol expression. And then when you define a type using the def type expression, then you say what protocols this type implements and the functions from those protocols. And so that's how you define a type, is that it's a set of values that implement these functions. And you can also extend types to implement protocols. If you didn't develop a type, if you're pulling it from a library, you can declare a protocol and extend that somebody else's type to implement your protocol. Had another point, forgot what it was, never mind. Okay, this paper, or actually lecture by John Backus, super interesting. Back in 1977, he said basically, write small programs and then compose them. Have an algebra for composing small programs to build larger programs. And that was in 77. And I'm sure somebody can correct me if I'm wrong, but Moggy didn't describe monads until 91 for composing stuff. So Backus really had foresight in his Turing lecture, and I would encourage, and it's a pretty easy read. You can skim the paper without delving into a lot of really gnarly stuff. You can skim it and get some really good ideas and just get a flavor. But he really was forward thinking because he had just come out of designing Fortran and basically said, we screwed up. So I would recommend that, reading that. So the reason it's called Toccata is because I wanted to emphasize composition. And so I thought fugue, I'll call it fugue because fugue is a composition. And we've all started GEB. At least I have. And so fugue, and then a fugue computer language, somebody already took it. It's like, okay, Toccata. It's kind of associated with fugue. I don't know what it means, but it's kind of there. And so Toccata was the name. And then at the speaker's dinner, Paul Snively gave a vast, detailed explanation of the relation of Toccata to fugue, and it sounded really nice. And I was like, that's why I did it. Okay, so programming by composition. So first of all, just simple composition, putting two things together of two values of the same type together is done, or actually two or more, can be any number, is by this composition protocol, which is just the monoid. Comp star is just smashing multiple things together, and you provide a zero. If you don't provide a zero, then you get like a semigroup. But one of the whole points of this, of the whole thing, was when I came to functional programming, as I was learning closure and stuff, I was like, I kept hearing this word monad. And so I embarked on a quest to understand monads and detoured to understand arrows first, which was a mistake, but anyway. But all this terminology just confused the heck out of me. And yet the ideas are pretty simple, at least as working programmers can make use of them. And so in Toccata, I want to steer away from using complex or mathematical terminology while still letting the concepts come through and providing those to the users. So yeah, it's just a monoid. Okay, so then category theory is all about composing things, composing functions and morphisms and all kinds of weird things. So the container protocol just defines the operations for the category, functor, applicative, monad, comonad. And by the way, you guys have been doing great throwing out comments, but feel free, I'm not thrown off by that. So yeah, you have the container protocol. So you have composition, container, and then collections. And basically a collection is something that you can reduce. And so that's the reduce protocol function, but then there's some other functions that are handy to have with containers or with collections. Mm-hmm.
If you're defining a container protocol where the container is both a monad and a comonad, isn't the only container you can define a simple box?
So you don't have to define every single protocol function for a type.
So just core dumps if you don't?
Yeah.
Okay.
Yep. No, hopefully.
Who needs type safety?
No, heck no, you don't need type safety. Types. But yeah, wait till the end. I think there's something that you'll like at the end.
No.
No, I'm serious. I think you'll like it. And if you don't like it, I would like to know why. Okay, so composition, container, and collection seem to be the three protocols that let you really nicely encapsulate the different forms of composition, at least in the work that I've done so far. Now, I am not opposed to defining other protocols as they become apparent, but it just seems like those three protocols really sum up what I was trying to do. And then there are some other utility protocols like function semantics and ordinal and eq and that kind of stuff. Okay, so I like Lisp. I like having macros, but I also want something more. And one of the things I wanted more of was being able to work with the AST directly, as easily as it is to write a macro in Lisp. So a macro lets you plug into the compilation pipeline after the reader or parser has parsed the text, before and then parses it into the nested S expressions. You get a chance to muck with those S expressions before they get handed to the analyzer. And then the analyzer produces an AST and does the code emission and whatever. I wanted a chance to muck with the AST after the analyzer had gotten it, but before the code emitter got it. And so I haven't even defined a macro system for Takata yet. I intend to, but I can only do one thing at a time, so I haven't yet. But I do have this mucking with the AST facility, and I'm pretty pleased with the way it worked out. So the analyzer, like I say, produces the AST. There are a number of primitive AST types. As you can see, a couple of examples, AST node for a symbol or a keyword, whatever. And these are typically the leaves of the AST. So you have a tree structure, the leaves are AST types. Now there are some internal in the tree node types that are AST types that define part of the tree structure. But yeah, by and large, they're on the leaves. So then you have this AST, this tree structure, and so you just hand it off to your emitter. And the emitter is actually a protocol function. It's actually called emit C, because I'm emitting C. And each of the data types in the AST tree get extended to implement this emit C protocol function. And so as you traverse your tree, it knows how to emit code for each node. And so it spits it out. So you evaluate the tree using that protocol function. So if you want to modify the AST, you just define a different protocol function and extend those data types to implement that function. And then you evaluate your tree with that function instead of the code emitter. And instead of spitting out code, it spits out another AST. Make sense? And then you can chain those together, multiple rewrites until you produce the final AST that you're going to hand to the emitter.
So I take it that your, I'm just sort of reading into this, but I'm assuming that your functions then have some form of sort of advanced deconstruction, pattern matching, then for you to be able to define an extension for a particular rewrite rule that might involve multiple tree nodes.
Mm-hmm. So that's part of the protocol. It dispatches on the type of the first argument.
But
and then,
only the type, you don't have the ability to reconstruct beyond that?
Right.
Okay, so for an example,
Mhm.
right? If I wanted to write a rewrite rule that like looks for 2 consecutive additions on literals and like merges them together, I would have to like extend the addition node and like, you know, muck around inside of here and maybe do nothing, as opposed to like specifically extending, well, addition with addition on the right.
Yes, you do have to do that, and I do have a pattern matching type construct in the language, which is separate from protocol dispatch and whatever. But yes, you would have to in the, it's an applicative tree, so in that applicative node, which has the 2 literals as the children, then that function that you extend that type with would have to see that it has 2 literals as children and produce a node that would get plugged into there. Does that make sense?
Yeah, and then just basically produce identity if it doesn't apply.
Yep.
Yeah, okay, that makes sense. Or
Okay.
core dump.
Or core dump.
Choices are good.
Yeah. Okay, so just a side note, look at the RR project. Robert O'Callaghan, I think his name, from New Zealand. What it lets you do is instrument an executable on Linux only, sadly. And it records the trace. It records the program. And when you core dump, then you can go back and replay the trace and multiple times and look at state all the way through. It sounds super cool, and I really hope to implement it as one of the debugging tools. Okay, side note. So yeah, it currently emits C code, but there's no reason it couldn't emit anything else you want. Python, whatever. But then you can also take an AST and spit out some kind of HTML for literate programming. Or write other tools that work with your source code quite easily. And I'll give an example or two here later on that I intend to write. Okay, that was all kind of the mundane stuff. Now for the cool stuff. How am I doing on time? I should be going through pretty fast. Half an hour? Perfect. So for the cool stuff, no build tool. So Clojure has Linigan. I guess Scala has SBT or something. There's Make. There's other things. I don't like build tools. I don't get those things. So you should, in my opinion, you should have your source file and your compiler.
Ideally one source file?
Ideally, at the root, you have one source file.
Oh.
And you hand that source file to your compiler, and then it should produce your executable.
And it traverses and finds the other files you're including?
Yes. So in your code, you say module, and you give it a file path. And that can be a relative file path, or it can be, from root or whatever. And when the compiler hits that expression, it goes off and grabs that file and compiles it. Or actually reads it, parses it, produces an AST. And then the result comes out, what comes out of that expression is just a list of ASTs. And then you can do things to that list of ASTs before it gets handed to the compiler to actually emit code. And so like you were saying, you start with a single file, and it goes out and finds all of the modules in a tree. And if you try to load a file twice in multiple places, it just memoizes that, and so it doesn't try to do it again. But yeah, no build tool, no anything like that.
You made an early dependencies that you have to fetch from the net.
That's the next piece. Was there some other comment?
I'm going to ask if you made an effort to cache ASTs between runs, the subtrees.
Between runs? Probably not. Could, but probably not. So you have the tools then to walk your entire project tree and do things, because you can rewrite the ASTs. You don't have to emit code. So I'll get to that in a second. So you take this module expression and you put it inside of an add-ns expression. And that add-ns has to take it, you have to provide a symbol which then prefixes any symbol that gets defined in your module for that module that you're importing it into. So there's no anonymous imports, name collisions, whatever. So if you haven't picked up yet, I'm kind of opinionated about certain things. And I really want to force new people coming into using this language in a certain channel to hopefully keep them from going off in tangents and get closer to where they want to be faster. I could be wrong, but I'm not.
Welcome to building a language.
Yeah, exactly. So yeah, and the file names that you put inside of these module expressions are totally unrelated to the symbol, the namespace prefixes. So there is no correlation between file path and namespace name. You don't have to remember to put an underscore in your file name in place of a hyphen in your namespace name, because there is no relation. Okay, so you have your source file, you have the ability to walk it, you have access to the analyzers and stuff, so you could walk your tree. You're given a file, you read it, and transitively go to all of its modules it imports, and if a module gets pulled in somewhere in your project, you can mock that out with a mock module for testing. And that happens way up at the top. It has no bearing on your production compilation or whatever. This is part of your testing framework rather than your compilation or your build system or whatever. Okay, and you can do all kinds of things. Anyway, I'll leave that up to your imagination. Okay, you're not limited to just modules with Takata source code.
So if there's all these things I can do at compile time, you must have some build system that is, I'm configuring something. Am I just writing C code to do it?
Nope, you don't. You have the compiler.
So am I writing the compiler whenever I want to make a change? If I want to mock in my...
Yes.
Right.
Yes, you do, because that's the whole point of having access to the AST. You get to plug into the compilation toolchain.
Well, but you say plug in, so how do I configure the plugin? Or am I just rewriting the compiler?
You're in essence rewriting the compiler, but it should be easy.
Correct me if I'm wrong, but it sounds like your source code is part of the compiler.
Yep.
Because it's loaded, and you can manipulate the ASTs, which make up the rest of your program, at compile time.
Yep.
So you are, in a sense, it's like the compiler is only part of the equation. You put the last piece in place, which is how to assemble your program thing. So you're writing the last bit of the compiler.
And is your compiler self-hosted?
Yep, it is now.
Well, that's what, so it's its own build system.
Yep. So, but, and this would require, I put the slide in because it'd be cool, and then I realized, oh, well, wait a minute, that needs a new AST node. But that's really not too bad. And so if anybody wants to do something like this, I will be glad to help them, and it really won't be a big deal. But yeah, you could have a Python file, and if it obeys certain rules that you define, and you define a parser or a grammar for Python, so that it spits out a list of nested S expressions, then yeah, you can import Python code directly into your project.
Seems like you could kind of step back from that a little bit even and just have a very, very general and powerful FFI where, you point it out like a jar file and it imports class signatures and the ASTs that it gives you are functions that will delegate to those signatures.
You could. And so this kind of raises the question of exactly what is Takata? I mean, if you can replace the front end and you can replace the back end, do you still have Takata? And so for my purposes, I'm defining Takata as a particular front end that compiles this Lisp language and a particular back end or a particular AST, and then it will target, in this case, C, but then eventually perhaps Python, or so whatever you target on the back end is kind of you swapped out and still call it Takata. It's more the front end up to the code generation that has to be fixed. But I am not opposed to anybody, writing a Python to JavaScript transpiler using these tools. And if you want help, give me a call. Okay, dependencies. You asked about dependencies. Okay, I do not like the idea of a centralized package repository like npm or clojars. So dependencies are just any Git repo or any Mercurial repo that's out there. And so instead of having a module expression, you have a Git dependency expression. And you give it a file path inside the repo, the URL to the repo, SHA, and a branch. And you can give some subset of those parameters to start with, yeah.
Why is the branch and the SHA required?
Because if you have a SHA, then obviously you can build an artifact. But if you update, if you want to go to a later version of that dependency, you need a way to know what the next good version is.
Other than literally browsing it.
Yeah.
How do you sell it to like diamond dependencies where 2 dependencies use like different versions?
Perfect. Let me see if it's...
Corda.
Actually, no. Well, I think it's in a slide, but I'll tell you. Because you're pulling in source code, it doesn't matter. Pulling in 2 different versions of the same dependency is like they're totally separate dependencies. Totally separate.
If you're passing data structure from one that's expected to slow into the other.
Because there will be different types. They will be tagged as being totally different types.
Yeah, okay, so that's basically your problem, that it's not going to compile.
It'll compile.
Yeah, it's Corda.
But when I get one from module A and pass it to module B.
Except you won't pass it to module B. So a dependency will define a data type. And it will say, and by defining a data type, it will say these protocols are implemented for this data type. So anytime you call one of those protocol functions with that data type, it will go to that implementation. If you have a different version of that dependency that defines that same data type with its implementations, and you call those same protocol functions with a value from that other dependency, it'll go to those implementations rather than the other.
I'm assuming that the protocols that a particular type implements are static, though. They don't change over time.
No, they don't. They're static because it's statically compiled.
Yeah, we use like change between different versions of a dependency.
Well, yeah, but they're literally two separate like they're totally separate libraries.
It's like every dependency lives in its own.
Right. So
Heaven forgive me, OSGI container.
NPM or something. But
Yeah.
sure, but if I'm getting a value of one of these things from one kind of transit dependencies down here, and I'm passing it down to.
But you don't pass it. You never pass it to anything else. You just call a protocol function on it. You never pass into another module. And if you do pass it in, it will call a protocol function on that value that you passed in, and it will go to the proper implementation that was defined in the other dependency. Yeah, back here somewhere.
No, it was the same question. I mean, unless there's some special shooting for like namespaces. I mean, like I've thought about this idea, but I always imagined that when you're like kind of importing it, you need to like prefix it with the version or something like that.
Maybe it's back a slide. So if you remember back to the add-ins expression, you have to provide a symbol that will prefix all the symbols that come out of that dependency. And
so you're basically naming the...
Yes.
Okay, then that makes sense.
Yep.
And,
So
okay.
Have you looked at Nix and thought about how Nix relates to problem space or something?
I know about Nix.
Okay.
I have not looked at it.
Okay. I think it might influence.
It is very intriguing, but hey, what can I do? Was there some other comment? Okay. Okay. Now here's to answer your question. I hope. Assertions. This is my own bias, and I could be wrong. But I do not like having to try to program at the type level and the value level separately. That's just a product of my history. Um,
So you want vigorous?
maybe. So, yeah. So you start programming with Lisp, and as the Lisp model, and you just dynamic types. You kind of explore your design space. You get something that kind of works. Eventually, your design is going to firm up. It's going to be firm, and so you add runtime assertions to say, this value is an instance of this type at this point in the code. And at runtime, this gets checked. And if it, is wrong, it core dumps. And this is something I think I can do, and maybe people will tell me, but I think you can use an SMT solver and look at your code and determine which assertions are redundant. And if they are, then you just optimize them away. And so you have, that's basically your type system. And then, so it's kind of gradually typed. And the problem with gradual typing, one of them, is you can start with a dynamically typed program, and it runs very well. You start adding contracts for the gradual typing, and performance goes crap. And but then until you get all of your program under contract, then performance comes back because it eliminates stuff. So
Well, I would hypothesize, and I don't actually know of any rigorous research on this subject, but I would hypothesize that phenomenon, which I see it, is because people start adding their contract kind of from the inside out, and so things kind of show up in their hot path. And with most gradual typing systems, like core types, for example, like when you go into it, like it has to check the contracts at the boundaries, and then inside it's great. But if you're doing that contract checking inside of a hot path, it's
exactly.
Screwed. So it's not necessarily that you have to get like your whole program under contract. You just have to get like to your large chunk boundaries, and then you're fine.
Yep, exactly. And actually, I saw a paper. I didn't read it, but I saw a paper that described this problem, and that was. So there are papers out there that they've investigated this, and that's one thing that gave me this idea. So assertions can test any condition. You can put any kind of code in there you want. The compiler will come along and see about the expressions that it can recognize and make use of at compile time. And anything that it can't at compile time, it will leave to runtime. And then as I get smarter, I can expand the universe of assertions that it can recognize at compile time, is the idea. So then there's a separate tool that you can run on your code, and it will give you hints about your hot path and how to get more and more of your program under contract to improve performance.
How is it different than an optional typing system if you just described like when you declare a variable to a list?
It probably is an optional typing system. So I don't know that it is different. And so what I like about it is the syntax for the type level programming and the value level is the same. It is the same thing.
Is this to say dispatch is always dynamic?
Yeah. Except,
Despite knowing the type to some degree, you can't stack it, right?
well, no, actually I do.
Oh.
And even now, under the covers, I don't have the assertion and all this mechanism in there yet. But at the very low level, where I actually wrote a chunk of C code to create one of the primitive types, the compiler keeps track of that type that was produced by that expression and tracks that all the way through the call tree. And so anytime that it compiles a call site and it knows what the dispatch type is or what the types of the arguments are or whatever, it will compile an efficient call site. It'll pre-dispatch, you might say, rather than leaving it at runtime. And I got a pretty significant performance boost out of that without having any types whatsoever, any type thing at all. So I thought, that's pretty cool. That was one of those moments where I'm a genius. Yeah.
When I attempt to program with category theory expressions, like it's very difficult for me to do it in Clojure because I need to think about the types first, and Clojure doesn't let me do that. Do you disagree with this approach?
No, I mean, if you come to problems like that, and you can put your assertions in first, and then write the code according to the assertions. So you don't have to do the code first. You can put the assertions in as like notes to yourself.
Do you have to run it to see the result of the assertion, or see if you violated any of the assertions?
No, you should be able to. Well, that should be a compile thing, and so it should be a separate tool. And hopefully, and I do not know about this, but hopefully, you can extract other models out of your code to check. So like maybe generate random values for generative testing automatically. So that you just write your code and then say, I want to generatively test this function that I just wrote. And there will be enough information to go to generate a bunch of inputs and test it.
So I'm confused. So if the assertions are done dynamically, you need to run the program to find out which path you took. So how do you write a type checker for that?
So they start off being run dynamically at runtime. But then you can have a tool, part of the compilation tool.
But your program is a monad. It's not an applicative. You can't inspect it without running it.
You can inspect the types.
Can you?
Well, that's a good question, actually. So,
Optional typing is some of them.
I think it depends how you write your code.
The types depend on the condition. You
And
can't-
it's not all of the ASTs being like dynamically generated from some random database somewhere. Like there's still like ASTs that are being generated from syntax that's in a file. So the compiler can see that. So your program, yes, in principle, is like a dynamic set of ASTs that are being loaded, but it's right there in this particular case, so the compiler can see it. And so that can be statically checked.
So that's like why the inside-out approach is so important. Okay.
Yeah.
Oh, so I guess I'm unclear on whether like what you're proposing really addresses this person's concern, because I know I've run into this problem too, right? Like where, you know, if you're writing something with like, you know, complicated monads or whatever, you really need the type system to help you figure out what you're even trying to do, right? And so like, you know, writing the assertions that describe what my code is supposed to do would be just as difficult as writing the code, right? Like, you know, I don't even like know what I'm trying to accomplish when I'm trying to write this kind of code, and I need the type system there to actually like, you know, guide me towards the like one logically correct thing that I could be doing.
sure. Programming is hard. and I don't really mean to be flippant, because programming is hard. And I do not have the skills to design the programming language that we need to be using in 10 or 15 years. What I hope to do is push us toward the next step. And so it kind of a scope is somewhat limited.
Well, we can add more to the type system because
You absolutely can.
Or have an AST there.
That's exactly right. And that's one of the purposes of being so open, is that hopefully other smart people can do things.
I have something of complete crazy time here.
Sure.
So you showed some examples of like, or you showed an example of like an assertion we're saying like this instance is a list, and that assertion is like a discrete thing, right?
Mm-hmm.
And presumably you might, for other parameters, say like, you know, this other parameter is like a string, and then like you know, at your final result you might say it's like something else. So that's sort of expressing a function type signature, but it's highly first order. Is it possible, like how would you envision expressing a polymorphic constraint? Like can you represent the function type, you know, A to be A? And how would you do that? Because your assertions are separate things.
I will have to think about that. But maybe this will be part of the answer. Okay, so you have protocols defined. And a protocol is a collection of function specifications that the implementations have to work together in some form. So you can assert, like the monad laws, inside the protocol definition. And that says that any implementation of these protocol functions have to obey this relationship. So that in this case, flatmap wrap x4f is equivalent to just f of 4. Does that make sense?
Can you put free variables in there? It's like say, instead of saying 4, say like, you know, I don't know, ampersand y or something. That's like a new variable that's introduced. That's unified.
Probably. I mean, heck, this is all vaporware. So I read the little prover, and I was like, oh wow, you can do this. that was my first introduction to actually proving stuff. I was like, this is so awesome. And so it's like, I want to do this. And free variables, I don't know, maybe, probably. I would think so.
And Mini Cameron can, so I would assume so.
Well, yeah, if Mini Cannon can do it, then yeah. So there are 2 libraries that I'm going to implement right off the bat as soon as I get just a little bit further. Property-based testing and Mini Cannon. Those are, because I need Mini Cannon to do the assertion type check. It's a logic programming library.
How's that spelled?
Mini, M-I-N-I, Canren, K-A-N-R-E-N. It is described in the book called The Reasoned Schemer by Dan Friedman and 4 guys.
So to help me understand, so for the free variable, if you try to unify it, it would try to find it would try to generate a situation that proves it false. That's not a proof. Or is it possible to do this actually as a proof? Rather than searching for something.
It's possible to do it as a proof under a lot of circumstances.
Even hooked into his language though, because it's using his flatmap function.
So, yeah, so you define an assertion like that in the protocol definition. And that assertion at that point says any implementation of flatmap and wrap has to obey this relationship. And so when somebody comes along and implements flatmap and wrap for their custom data type, then it goes through and it will have the ASTs of their implementation. And then it can plug those into this system of trying to mangle those expressions with those ASTs using substitution until you get an equality, or you prove that you can't get an equality.
It would also forbid impure flatmap if you have that kind of assertion, because you wouldn't be like as soon as you hit some sort of impure block, like you can't do substitution anymore. So you just
That's it. So that's me, and that's who I am. So this is totally vaporware. I would love to have input.
I know being a colleague of yours that it's a little bit more than vaporware. Can you actually show, do you have enough with you to show anything?
Okay, bear with me if I can figure out.
I mean, there are probably more questions than that. There's some other questions.
I think John just.
So here is the compiler. Actually, this is the to-do list at the top of my compiler.
That's like the same as compiler.
Pretty much. So that was my to-do list. And then here is the beginning of the compiler. And it's all written in itself. And so you see I bring in some modules, prefix their namespaces, start defining some of the C code in the strings that will get plugged into the emitted C code. And then it's just a bunch of stuff. Like it goes on and on and on and on and on. Anyway, yeah.
I'm wondering because you mentioned that so you're producing C code and then you're using C line to produce, to eliminate tail call recursion and just basically to produce binary. Doesn't LLVM have a kind of intermediate representation or something? I'm curious why you chose to target C when LLVM in theory designed this thing so that it would be like convenient to output to this thing, as opposed to C++, which is its own language. It's not a target for like intermediate languages. So what made you decide to target C++?
Because it sucks. So when I first started this, I wrote a cross compiler in Clojure to compile Takata to LLVMIR. And it was hard, but I got it working. And then I needed to be able to debug the output of the compiler, which is much easier to do as a C file than as an LLVMIR. So, yes, you're exactly right.
They kind of fail with their LLVMIR. I mean, if it's more convenient to go to C++, I mean,
Yeah.
Well, this is the problem with all IRs, like Java bytecode included. If you write a compiler that targets Java bytecode, you will actually become enormously good at just reading bytecode straight out.
Yeah.
You just read it straight out like any programming language. So you have to be able to do that with LLVMIR as well, and that takes time. Like I agree with you. Like I think you should be compiling LLVM, but
and I will.
It's a problem. Like,
So I just ran my standard test, which recompiles itself 4 times, and it takes about 6 seconds, 6.1 seconds to convert the Takata source to the C source. So there you go. That's a little bit of the non-vapor aspect of it. So, and this is all on GitHub, like I said, not very recent, up to date, but it will be. So thank you very much. Hit me up.